Hello and welcome to the another series of coding. Today we will solve LeetCode problem, common ancestor of a binary search tree. Okay, so basically what the problem is given to us, we have to find the common ancestor between two nodes. Okay, so what is ancestor? Ancestor is a node that is above than that node. So suppose that our our node was 9, then ancestor of 9 will be an 8. Okay, so this is ancestor. And this problem is saying that you have to find common ancestor between two nodes. So let me take into the demo board. Okay, so suppose that our n1 node is given as 10. Okay, 10, and n2 node is given as 14. Okay, so and question is asking find the and common ancestor node, right? So what one naive approach is that we will find the path from root to that node. This is n1, right? This is n1 and this is n2. Okay, we will find the path from root to n1. Okay, and we will store this in some data structure. Okay, so n1 path is n1 path. Okay, so 28, 12 and 10. Okay, and n2 path will be this. N2 path will be this, right? So n2 path equal to 28 and 12 and 14. Okay, so and we will find the common. So in this figure we can directly say that this is a common ancestor node in this between 10 and 14, right? So in this we will traverse from back. Okay, so and traverse from back, whenever we get the common node we will return it, right? So we will traverse, we will from this and this is not common again, and we get this is common at position third, they are common, so we will return it. Okay, so we will return 12, and 12 is the common ancestor node between two paths. Okay, so this is naive approach, and this approach require time complexity of order of n cube. First you will find the path from root to n1 and from root to n2. After that you will traverse the both the arrays to find the common node. So it will require order of n cube. Okay, time complexity, and it will required space complexity of order of n. You have to store the nodes in some data structure. So this is very naive approach, and this is not so efficient approach. So what approach you can apply? Let me oh, so you can use the recursion to this do this problem. Okay, so okay, so what we will do, we will create a we will call the function recursively again and again. So this is our recursion definition. So what we will do, if the root will be none, we will return none. Okay, our n1 and n2 are n1 equals to 10 and n2 equal to 14, right? This is our query. So what we will do, we will compare n1 and n2 with the root. Okay, root value. So we compare that n1 is also less than root and n2 is also less than root. Okay, so this is binary search tree. We will go in the left side of the tree. So root become this. Again we will compare with n1 and n2. So n1 is also greater than root value and n2 is also greater than the root value. So we will greater, that means we are going into the right subtree. Okay, now we came in the right subtree. Now root become this. Root become this. Now we will compare n2 and n1. Okay, n1 and n2. So n1 is in the left, is smaller than this. Okay, n1 is smaller than this and n2 is greater than this. And whenever we will encounter this situation, whenever we will encounter this situation when the root value root okay root what the heck is this, we encounter this situation that 12 was the root and n1 is smaller than the root value. Okay, and n2 is greater than the root. Okay, so what we will do, we will return it, we will return the root, we will return the root. Okay, as simple as that. Okay, so what is the time complexity of this? Time complexity of this is order of n. What is the space complexity of this? And the space complexity will be auxiliary space, that is order of n, and if you use the iterative method it will require order of 1, because in the recursion you have to maintain the recursion stack and that will require order of n space. So it is auxiliary space. Whenever function call will end, the space will be removed by our garbage collector. Okay, so let's take another example. Okay, first there are basically three condition. Okay, for if the root, if suppose that if the root n1 greater and n2 root is also greater than n2, right? This is for first condition. Okay, then we will go on the left subtree, right? So we will recursively call the function on the left subtree, so root dot left. So okay, this condition 1, this is our condition 1, and another condition, second condition is if root is smaller than n1 and root is smaller than n2, we will call on the right subtree, right? Okay, and if these both conditions are not satisfying, then we will return that root. Okay, suppose that means we are in the condition that n1 is smaller than the root and n2 is greater than the root, and this is a common ancestor. Okay, so we have to remember these two conditions. If root is greater than n1 and root is greater than n2, so we will go on the left subtree. If the root is greater than n, if the root is smaller than n1 and root is greater than is smaller than n2, then we have to go on the right subtree. Okay, this is the basic logic. So let me let's do program. Okay, so what we will do, we will make it recursively call again and again. Okay, so what we will do, we will, if root is none, if we say that root is none, then that means nothing is there in the tree, so we will return none, return none. Okay, and so first see this, it required no a tree node. We will return whole node. If our answer is this, then we will not return the data value. Okay, we will return this node to our okay. So if root dot val, first condition is that root dot val is greater than n1. Okay, so here is p n1, and root dot val is greater than q. That means we are going in the left subtree. So root value is greater and then the both values. So this is condition first. Okay, so we will call this function on the on left subtree. So return lowest common, and we will say root dot left comma p comma q. Okay, and second condition was that if root dot val, and don't forget that these are tree nodes, so we have to compare with the values. So where we will write where values value. Okay, val and greater than. Now we will come here in second condition, root dot val and root is smaller than our n2, then we will call on the right subtree. Okay, return root dot right, and we will pass p comma q. And if these two conditions are not satisfied, that means we found our lowest common ancestor. Okay, and we will just return our root, and that's simple like that. Okay, let me run this program. What is the lowest common ancestor? Oh sorry, we have to use self because we have to pass an object. Sorry, self. Okay, now it will work fine. Okay, it is working. Let me submit it. Okay, this is working and it is pretty efficient. It require order of n time complexity and order of one space complexity. Okay, and thank you guys for watching.